Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, thank you. So this is a very grown-up and serious title, but in fact, it is going to be a brief report about me trying to apply quantitative verification in the context of molecular programming. So we've already heard about molecular programming from Udi Shapiro and Andrew, etc., and this is something that Luca is working on. And before I say something about molecular programming, I wanted to say happy birthday to Luca, and also thanks to him for inspiring me to work on this topic. I started working in systems biology, applying PRISM and probabilistic model checking there around 2005. This is another Festschrift for Grzegorz Rosenberg. In 2009, this book appeared, and this is a collection of papers that were written, as you can see here, but virtually most of the key researchers working on natural computing, not just molecular programming, but natural computing, to honor Grzegorz Rosenberg. Now, in fact, I didn't realize until some years later that Luca was also invited to work, and his artificial biochemistry paper appeared there. And here is my humble quantitative verification paper. But in fact, there was also our current experimental collaborator who was invited to contribute a paper to this, Andrew Turberfield. So happy birthday, and thanks. Okay. So what we are doing is we are working at the nanoscale. So this is, where you measure things in nanometers. And I'm showing you examples of molecules that I have been working with. So when I was working in systems biology, I was working with biologists on this, on predictive modeling for this human FGF protein for signaling. And now I'm working with experimentalists and also with Luca and Andrew and my group on with DNA molecules. So what can you do from DNA molecules? And this is an example. Here you have a real picture of the artifact. What you can do if you take a very large, long circular strand of DNA, and this is something like 2,500 base pairs. This is what is called a monomer here. And then you also throw in so-called staples, shorter strands of about 15 to 16 nucleotides, and you select them so that they are complementary. Then when you put everything in a solution, they will form this shape. As you can see, there is this join here, because the staples will pin the large strand, this large circular strand, in place. So this is called origami. And in fact, we are trying to understand the scientific principles behind forming of the origami structures. But in fact, what I wanted to talk about is molecular programming. And molecular programming is a term that I think was invented first by Masami Hagiya, and it's big now at Caltech. There is a molecular programming project there due to Eric Winfrey. And the idea is that what we want to do is we want to program with molecules. And for us, computer scientists, this is very interesting and also very similar to computer networks, because we have networks of molecules. They can interact, but they can also move. So we can talk about motion and robotics in that context. Now, the key observation is that they are programmable, and that the computation proceeds autonomously. And of course, this is an ideal playground for people like Luca, because we need programming languages, and also for me, because we need probabilistic quantitative verification. So I'm just going to now say that what we do is we focus on programming with DNA molecules. Why? Because it's very versatile, it can store information, it's also very cheap to synthesize. You know, even if you need to synthesize thousands of base pairs. And it is also a very good medium for designing biosensors. So if you want to detect the presence of absence of a particular molecule, the idea is that you can design a molecular program to do it for you. And I'll show you some examples here. But of course, because of Moore's law, we know that we need to make computers smaller, so there is also an additional interest for computer scientists. And because they move, you can make molecules move, we can talk about robots at the nanoscale. Now, there are many applications that have been envisaged, and these applications involve not just designing networks from molecules, but also placing these networks on these origami structures that I've shown to you. And this is what I'll tell you about. So I really, want to talk about what good quantitative verification has been. What have we managed to show so far? And I'll finish up with some challenges. And of course, because we are talking about molecules, stochasticity is essential. And in particular, I work with discrete stochastic models, in particular, continuous time Markov chains, and something sometimes more complex than that. So I'll say something about what we've done, and this is in a setting focusing on DNA programming, where there is the DSD tool that Andrew told us about, but also there is the PRISM model checker that was developed in my group, which can be used either as a backend to DSD, or it can be used directly. And I'll just show you how, the progress over the last 3 years. And I'll finish off with challenges and directions. So DNA circuits, we can use DNA to design computational circuits. Now, we know that conventional silicon circuits compute with bits, 0 and 1, true and false. DNA circuits are very different. This was called computing with soup in an article about Andrew Phillips. And the idea is that inputs and outputs are these single DNA strands. And then when you design them, then they'll bind and unbind and compute something. So in fact, a circuit that can compute the square root of a 4-bit number has been demonstrated. It takes 10 hours to compute, but it was the first one. And this is why we started working on molecular walkers, because it's a faster technology. So how did I get, this is a blog reaction. This is not mine. This is how the blogs reacted to this paper in Science. So how did I get into this? Well, in fact, Luca was aware that we were using PRISM in systems biology, and he suggested that we look at the design of his transducer. So in this case, we are working on DNA computing with a restricted class of DNA strands. They are 2-domain strands. So what we have in this is we have double strands with a short toehold overhang to which another, a matching complementary toehold can bind. But we also have these single strands which are 2-domain because they have a toehold attached, and the toeholds are used to ensure reversibility of the reactions. Now, Luca's contribution to this was to design a process algebra, DSD, and then Andrew implemented the tool. And we have worked both with the tool, but also we have worked directly with PRISM. So what we did is following Luca's encouragement, we took his DNA transducer gate, and we managed to develop a connection from DSD to PRISM and demonstrate that there is a bug in the design when you try to connect 2 gates together. It is because of crosstalk. Now, this bug can be fixed, and it can be verified. Now, you might think that this is a great achievement, but in fact, Luca already found this bug manually, so our challenge was to demonstrate that it can be found automatically. Okay? Now, I can continue. I'm going to show you that in this probabilistic quantitative verification world, we don't just talk about probabilities such as termination. We can also talk about the probability of termination. So here we can show that the probability of error and success is the same. And this was something that was found with PRISM. But now I have a finishing master's student, and there is another design of biosensors, which is quite appealing at a high level. The idea is that we use strands as inputs, but we use the Watson-Crick complement to represent the logical complement. So a strand is a proposition, and now you also have the complement. And in that paper by de Murrieta, they have designed various gates for implication, and you can do reasoning, because there are various rules, and you can do it in a contrapositive. So if you have an implication, P implies Q. If you throw in not Q, you can deduce not P. So it's quite an appealing system. Unfortunately, there is a flaw in the design, and the flaw means that if you put in P and Q simultaneously, then it will deduce R correctly. If you put in P first, then Q, it will work. But if you put in Q first and then P, it fails. Okay? Now again, you might think that this is a great achievement by my student, but in fact, Luca found this manually by reading the paper that I gave him. So again, the challenge was to show that this can be done with PRISM. But in fact, the student has done quite a lot more work, I think, analyzing performance, which probably Luca can't do in his head. Okay? So for the final example is the molecular walkers. So I showed you the picture of the origami tile. What you can do is you can place tracks, which is molecules spaced out at certain distance and arranged into decision trees. And my experimentalist, Andrew Turberfield, he knows how to make molecules, place molecules at one end, make them walk, and also allow them to select branches according to whether something is present or absent in there. What we have done, because all these are planar, we have analyzed the expressiveness, and we can show that in fact these can, for this technology, they can compute any Boolean function. But in addition, what we've done is we have built this is Fritz, my PhD student, who is actually doing an internship here. We have built a CTMC model, and then we analyzed the reliability and performance and also various aspects of the walker. And the interesting thing is that this walker can actually deadlock. It can get stuck because it can only jump up to 2 anchorages. It can't jump up to 3. So for example, this is an example where it gets stuck because it has nowhere to go. Okay. And the final thing I wanted to say is what we have done very recently is we can now specify the parameter synthesis problem. In general, in verification, people are shifting from verification to synthesis. So shifting from the question, does the system, the model, satisfy a formula, to a question, can you give me the model that is guaranteed to satisfy the formula? This is a difficult problem, and maybe near Peterman here I can tell you more about this problem. We are looking, especially in the quantitative case, we are looking at the simpler problem, parameter synthesis. So if I have a parametric model, can I find the valuations of the parameters so that the formula is guaranteed to be satisfied? And we have developed an algorithm which is based on successive region refinement and implemented it and applied it, amongst others, to the case of the walker. So we can subdivide the region space, and the green area is the area where the parameter valuations, in this case constant and sum rate, are guaranteed to satisfy a given reliability requirement. And this is the end. So I have shown you what we have been doing by applying quantitative verification in molecular programming. And the idea is longer term, is to design, to incorporate it in design automation tools. And I have also shown you some successes. Some of our predictions have been confirmed experimentally, but scalability is a huge problem. So in particular, for many of these well-mixed solution molecular programs, we stop at, can you guess how many molecules? 7. Even though in a real solution in a test tube, you have billions. So this is the scalability gap that we verification researchers have to address. So that's, okay, thank you.